Swayam Prabha. Digital India. Educated India.
So far we have discussed about the equation of motion in the last class. And we also have discussed about statistical mechanics and the modeling part. So, this modeling part is basically designing interparticle or intermolecular forces, which could be a function of particle-particle distance or the orientation. And then this equation of motion takes this potential model, and then you can write either a second order ODE, or you could write in terms of maybe I will write it. Right. So, either we can write in terms of a second order ODE or two sets of first order ODEs, where this potential goes as a input in calculating the forces. Then if we are able to solve these equations, then we are able to generate trajectories of the system. And once we have this trajectory of the system, then we can use statistical mechanics to measure thermodynamic or transport properties. So, that is the context we have been talking about in different sections. So, first we talked about various force fields, then we talked about statistical mechanics, and then now we also discussed about what is the classical equation of motions to advance the system's trajectory. So, now the question comes that how are we going to integrate these equations of motions so that the trajectory can be obtained. So, the question is about suppose if I know given that at a time t, if I know the information such as positions, velocities and accelerations of an n particle system, then how do we calculate positions, velocities, etc. at time t plus delta t. Okay, so that is a question that we want to answer. So, given at time t, we have the information of position, velocities and acceleration. Using that information at time t plus delta t, where delta t is the step increment in the time, and then you ask what is the values of these positions, velocities and accelerations. And once we know the information at t plus delta t, then we do again use this information at t plus delta t, and then advance the system to t plus 2 delta t and t plus 3 delta t, etc., etc. So, basically you integrate these equations of motions in steps using, let us say, some finite difference methods. So, we want to basically look at different kinds of algorithms of finite difference methods to do this. So, finite difference in time. Okay, so that is the context of this lecture is going to be. So, now there are many algorithms. So, first we will talk about predictor corrector algorithm, and later on I will introduce some other algorithms as well. So, in this case you can imagine that in the trajectory of the system is nothing but a curve where at each point at any time t, you have all the information of the particle positions and momenta, okay, for all the system of n particle system. So now this trajectory, if this were to be a continuous trajectory, then we should be able to write the position and momenta as a series expansion using Taylor series. Okay, so that's our starting point. So as you know, for any function of f of x can be, suppose if you want to expand f of x plus delta x about x, then you basically write using the first derivative and then second derivative etc., right. So any continuous function can be expanded as a series in Taylor series expansion. So we use this approach and then write analogous expression for the particle positions, momenta and accelerations. So that's one way we can make a first guess about what is the position, momenta and acceleration at t plus delta t, given that the information at time t is available. So what I'm going to do is write the position at t plus delta t using Taylor series expansion. And then this is basically an infinite series, it goes like this. So here this r here is the predicted, I am going to put a p as a superscript to denote it is a predicted position of an ith particle. I am not using this suffix I to denote for ith particle, but it is implicit. For every particle we write this kind of an equation for every species in the system. So, so the position, the predicted position at a time t plus delta t is nothing but the position at t and delta t times the velocity and then delta t square by 2 times the acceleration, and then you can have even the third derivative and fourth derivative of position as well. So using, so you can see that now we are using all the variables information at time t equal to time t to get or to guess or to predict the position at t plus delta t. And similarly we can also write for the velocities also. Again the p here means the predicted velocities. And then this acceleration. So here the v here is the first derivative, a here is the second derivative of position, and b of t is the third derivative of the position. So we using this information we can write a cascade of these equations where all these r, v, a, b, all these things can be predicted at a time t plus delta t. So now the question is these are just predicted values and we need to now correct them. Okay. So why we need to correct them is because in this particular prediction we have not really used the equation of motion that we talked about before. Okay, we have not related the acceleration to the forces and vice versa. So because of this, this predicted value is going to be little inaccurate. So we want to correct them. So that's the second step. So then, so what we are trying to do is in first step we make a prediction of the position, velocity, acceleration and the third derivative of positions, and then using this we are going to correct the actual position, velocity and momenta. So now what we are going to do is first, now that I have using the predicted new positions at a time t plus delta t, using this information let us calculate force at t plus delta t. So, remember this force is nothing but the spatial derivative of the potential energy, and the potential energy depends on the particle positions. So, now at time t plus delta t, we have made a predicted calculation of positions. So, using these new positions, we can estimate the force. Once we know the force, we can also calculate what is the accelerations. This is where this connection between the force and acceleration is being made from this equation of motion here. Okay. We know that mass times the acceleration is equal to force. So, if I know the force, then I know the acceleration. So, that is the correct value of acceleration at that particular time. So, we will use this notation AC at t plus delta t. Okay. So, now with this new position, we have got new forces. With this new force, we have got new acceleration. So, now there is going to be a difference between the correct acceleration and the acceleration that we just predicted using the current values of the positions. So, now let us write the difference in the acceleration delta A at t plus delta t as the difference between the corrected acceleration minus the acceleration that was predicted at a time plus delta t. So, now what we would like to do is using this difference in the acceleration between the corrected and the predicted, we want to go and then apply this difference in all this position, velocity and momentum, and then correct them as well. So, the way we do that is we write the correct position at t plus delta t is equal to the old or the predicted particle position plus some coefficient C naught times delta A, the delta A is coming from here, times delta t square by 2. Similarly, we write the corrected velocity with a new coefficient C1 so, you can see that so what we are trying to write is the set of corrected values using the predicted values of the position, velocity, acceleration and B, using the corrected the difference in the accelerations using certain proportionality constants C0, C1, C2, C3, which are supposed to be optimized so that this corrected value is close to the correct values. And so, this is where we get different sets of coefficients C0, C1, C2, C3 depending upon what is the order of the equation of motion and what is the order of the predicted corrected method. In one particular example of Geer's 4th order method, there are 5th order, 6th order method, but I am just going to give an example of a 4th order method. In this particular 4th order Geer's techniques, you will see this value of C0 is given by 1 by 6, C1 is given by 5 by 6 and C2 as 1 and C3 as 1 by 3. Okay. So, you so once you have these values C1, C2, C3, and then you can update the position, velocity and acceleration at a time t plus delta t. So, there are basically 2 steps overall. One is you first take the current values of the positions and velocities, make the predicted make a prediction of these new positions and velocities using Taylor series expansion. Once you have the new position, predicted position, use them to calculate the forces and then the acceleration, and then find the difference between the correct acceleration and the predicted accelerations. Using this difference, you go and correct the particle positions, velocities and accelerations with certain proportionality constants, and the proportionality constants value depend on what is the order of the second order, what is the order of the equation of motion that we are solving, and what is the predictor corrector method's order itself. So, in this particular example, the values of C1, C2, C3, all that is given for a second order ODE. So, if I instead of solving for second order ODE, if I do for first order ODE, these values will also change, and the gears of fourth order, fifth order, sixth order would also have a different set of coefficients. So, these coefficients are optimized keeping in mind what is the order of the ODE that we want to solve. So, so now let us see how we implement this in MD simulations. So, first thing is, first we predict A, V and C at t plus delta t using A of t, V of t and E of t, etc. Okay, that is the first step, and the second step is calculate the forces using this expression with the values of Rp known now, and then relating the acceleration to force by this equation, which is basically the equation of motion. And then third step is now correct A, V, correct R, V and A at t plus delta t. And at this point, if you want to calculate any thermodynamic properties, you can do that, because now we know the values of current values of position, velocity, everything. So, maybe if you are interested in energy or the virial or any other properties, we can measure them, and then you advance the time and then go to again to loop back to 1, and then you do this iteratively over many time iterations to advance the system in time. Okay. So, when you advance the time here, it will be going from t plus delta t to t plus 2 delta t, and then we just do over this entire looping. Okay. And this is how you generate particles position, velocity as a function of time. So, what we just discussed is one example of a finite difference method, which is predicted corrector method, but there are many other kinds of difference methods available in the literature with regard to MD simulations. So, now before we talk about other finite difference methods, we want to ask what is the required qualities or requirements of a good finite difference method for solving this classical trajectories of a n particle systems. So, we basically say that we want the algorithm or the finite difference method that we are talking about should be fast enough. What I mean by fast is that you should have minimum number of steps in advancing the system in time. So, you want them to be fast, and then it should use less memory space. So, what I mean by less memory space means the number of variables that we want to store, that should be as minimum as possible. For example, in the case of predictor corrector method, we have to store R, V, A and B. So, 4 variables we are storing at every time point. So, different algorithms will require different amount of storage space. So, that is also one of the important things that we have to keep in mind. The second aspect is this algorithm should allow us to use a large delta t. So, remember delta t is the parameter that says how quickly we are able to advance the system in time. So, if the algorithm allows us to take a larger time step, then we will be able to run the simulations for a given computing resource to a larger time scales. So, it is very important to ensure that the algorithm that we are choosing should allow the use of larger time difference delta t. And third thing is that this algorithm should be accurate. That is, accuracy is very important, and it should give the trajectories which is very close to the classical trajectory or the actual trajectory. As you know that we are talking about there is a classical trajectory, and we are trying to numerically predict this trajectory, and because we are using finite difference method, we want to ensure that the predicted trajectory is as close as possible to the actual classical trajectories. And like we discussed in the previous class, it should also ensure the conservation of loss, conservation of energy, momentum, etc., the linear momentum. Okay. So, this algorithm should not violate any of these conserved quantities, and finally, the fifth one is it should be easy to program or easy to code. So, these are some of the important qualities of a good program. So, now we want to basically look at you will see that not a single algorithm will satisfy all these conditions simultaneously. You will see that some algorithms are good in few points and it does worse in other requirements. So, of all these 5 important qualities, the most important thing for us in terms of MD simulation is that we want this algorithm to be able to allow a larger delta t. That is the most important quality. That is because we do not have to pay too much attention to the fastness, because in MD simulation the actual time consuming step is in the force calculation. So, anyway that is going to be limiting in the entire MD simulations. So, we do not have to pay too much attention to the fastness of the integrator time, the integrator. Okay. But on the other hand, this use of larger delta t is very important. And the third thing is about accuracy and closeness to actual trajectories. So, to illustrate the importance of how accurately the algorithm generates a trajectory, so what is shown here is an example simulation. So, first a simulation is done and it is used as a reference simulations, and then what we do is we conduct another simulation or set of another simulations where the initial particles positions are displaced with a little bit of a perturbation. Okay. So, first there is a reference simulations, and then we repeat the same simulation, but initially changing the particle positions little bit. Okay. The extent by which we are changing this initial position in those perturbation simulations is by an amount the particles position at time t equal to 0 is basically changed by some small amount delta, and this delta here could be of the order of let us say 10 power minus 3 times sigma, or 10 power minus 6 times sigma, or 10 power minus 9 times sigma. So, those are the different values that you see here. Okay. So, you are doing your simulations and then you are repeating the same simulations, but then slightly changing the particle positions in the beginning, and then you want to see compared to the reference simulation that we have done before, when I change this initial perturbation, how much difference is there going to be in the calculated quantities. So, in order to do that, what you can see here is we are plotting the change in the kinetic energy with reference to the original reference simulation kinetic energy for different amount of perturbations. The perturbations here are given. So, if you look at this figure B, you see that when the perturbation is very small of the order of 10 power minus 9, you see this delta k, that is the difference in the kinetic energy between the perturbed simulation and the original reference simulations is nearly 0 for quite long time, up to certain 500-600 time steps, and after that you see that the delta k varies quite a bit in time, okay, and it's kind of trying to diverge as time increases. Now, if we do the same thing for a larger perturbation of amount equivalent to 10 power minus 6 times sigma, then you see that this delta k remains 0 up to certain point, and after that it starts also trying to diverge. But if you look at the length of this instability occurrence, the larger the perturbation, shorter the time at which this perturbation develops. And then if you go to 10 power minus 3, which is even higher perturbation, you can see that in the beginning itself the kinetic energy starts diverging from the reference trajectory. So, what this tells us is that when we use a finite difference method to calculate the n particle system trajectory of two systems which are very close to each other, and we would think that if they are very close to each other in the time t equals 0, at any time in the future they should be differing from by the same amount as it was in the initial time, but that is not the case. You can see that at larger times the difference between the reference simulation and the perturbed simulations is basically diverging quite a bit. Now, another way of characterizing the same thing is you can define this delta r here, which is 1 by n sum over all particles. We take the absolute distance between so we calculate a quantity which basically tells what is the mean distance between a reference simulation and the actual simulations. So, this Ri naught here is the reference simulations in which the particle position I is taken, and then this Ri here is one of the perturbed simulations in which the same particle position is taken at the same time, and we find the difference between them. Suppose if this initial perturbation is not causing any issue, you would expect this delta r to be equivalent to whatever that was there in the beginning. But then if you look at this evolution of this delta r as a function of time in this figure A, you can see that when this perturbation is very small at time t equal to 0, you can see that it starts at 10 power minus 9 as you would expect, because initially that is our initial conditions. And then with the time you can see that this difference changes, okay, this difference increases, and then it basically diverges to a larger value as simulation proceeds further. Similarly, if you take the other perturbation simulations starting at 10 power minus 6, you can see it starts at 10 power minus 6 at time t equal to 0, but with the time you can see the difference between these trajectories starts diverging as well, and the same thing happens with larger perturbation also. So, what all these things means is that when we do MD simulations, we are using finite difference, and then in this finite difference we are rounding off numbers, we are approximating higher order terms in terms of delta t. So, at every time step we are making rounding offs, we are neglecting certain quantities, and all these things will have a consequence in predicting the trajectories. If the perturbation or rounding off error is very small, you can see that your simulation is going to create or generate a correct trajectory over a long time. But if this perturbation and round off error is large, and you will see this kind of a divergence occurring at quite quickly. So, for any finite difference method that we do, it is a good idea to do this kind of analysis to see if I want to do a simulation for certain simulation length. You can do this kind of a perturbation analysis and see how far the algorithm is able to produce a stable trajectory. That means any point which are very close to each other in the beginning should stay close to each other up to the simulation time that we want to simulate. But for any system, the moment you go to very large time scale, this trajectories will diverge. In fact, this divergence is exponential, and this is known as Lyapunov's instability, which is very characteristic of a dynamical n particle system. So, this is something that we have to keep in mind. And so, now the question is, if this is the case, if I am making a small rounding of error, or if I neglect small terms and if my trajectory is going to be unstable like this, so how is it reliable to do MD simulations is a question. But we don't have to really worry too much about it, because MD simulations we use to get equilibrium properties, and we calculate time correlation functions. So with regard to time correlation functions, all we have to find is that up to the time correlation function that we are interested in, the system's trajectory should be stable like this. Okay. On the other hand, if you generate any, if you use MD simulation to calculate thermodynamic properties, we don't have to be really worry about the correct representation of the classical trajectory. Even more important thing is that we have to conserve energy momentum. Those are the more important criteria. As long as the trajectory is able to conserve those quantities, and we should be able to generate ensemble averages from the MD simulations, because you may want to invoke this principle of ergodicity, which says the time average and ensemble averages are same. So you don't have to really worry about following the exact trajectories through the phase space, as long as you are able to conserve energy and then do a long time simulations and then average over, this should be okay. And the last point is about, like I was saying, this is the trajectory should be accurate enough, and at the same time the conservation of energy, linear momentum is more important. The final point is about the easiness of programming. So what this basically means is that it should use a minimum number of mathematical operations, and it should be easy to code irrespective of which programming language that you use. So the operation should be a simple addition, multiplication, division kind of an operation, so that's easy to program. So these are some of the important things that we have to keep in mind whenever we choose a finite difference method. So in the next class we will talk about various other kinds of finite difference method, and then whenever we talk about those methods, we keep in mind about its fastness, ability to do large timescale, large delta T simulations, whether it is accurate enough, whether it conserves energy or not, and whether it is easy to program or not. Okay, so these are some of the things that we want to keep in mind. Okay, it can be cut here. All right, so okay, here is some special information for the class. So what you see here is a nice pictorial representation of phase space that was given in Roger Penrose's book on the Emperor's Mind, I think. So what he says is that whatever I was talking about, this the divergence of the trajectories, it is nicely shown here. So if you take you can imagine this is a phase space, and if I take two trajectories which are very close to each other at time t equal to 0, okay, and you can see that for very small times these trajectories will preserve the difference between these initial positions. Okay, this is what I was showing in the graph in the class. But then if you wait long enough, what will happen is the trajectory will basically end up in different positions in the phase space. So here, once you have reached that kind of a long time behavior, and then now the question of starting from here and doing a time reversibility, we will never be able to reach this point, because we have lost so much information because of this rounding off error and various other numerical rounding offs. We have lost the property of time reversibility, and this also has a consequence I was telling you yesterday, that microscopically in theory we seem to say that we are able to predict any future or past given the current information is possible. But when you actually try to calculate, end of the day, using a computer, we end up with a finite difference method or any sort of rounding of issues that leads us to a lot of large information loss and gives a very chaotic nonlinear behavior that gives us a lot of unpredictability about the future. So as long as we are at a very close time distance, it seems that we are able to make a time reversible predictions, but in the long time we lose this information. A lot of information is getting lost, and you see this how the initial phase space, which is very close to each other, kind of diverges at large time scales. And this also has relations to the description of entropy, to what extent this initial 2 point is diverging at a long time point, that is also relevant to the calculation of entropy. and this is a reason why we are not able to do time reversibility for real non-equilibrium systems. So I thought I'll just add that comment here. Are there any questions now? So, but you know that any yeah, so that is true, but generally what happens is that the memory that you're talking about is related to the time correlation function. So memory, you're talking about memory of something, some property or some value, and so as long so when you say memory function, what you're trying to say is that the time correlation function is non-diminishing or non-decaying, right? So if that is the case, then that may be true.
Okay.
Yeah.
So I had another doubt. When you say that we use the predicted position values to calculate the force and then get the correct
Yeah.
acceleration values.
Yeah.
So how does predicted value give correct acceleration values? I mean, it's not supposed to give predicted.
Right. Yeah, you're right about that. So actually, what I did not mention in the MD context is that in the true predicted corrector method, what we actually do is we actually do this iteration. So what I'll do is I get this yeah, so I get this predicted value and then I get this corrected value, right? So then what I should be doing is right after the step, I will use the new positions, the correct positions, okay, and I again go back here, okay, get a new force, and then I iterate over and over until this convergence happens. But in MD simulations, such a repeatable or looping is not economical, so we do only one step correction. But in actual, if you go to predicted corrector method of solving differential equations, this is done in an iterative way until you get a convergence of desired accuracy.
Okay. So first the acceleration is converged and then using that
Yes.
rest of the quantities.
Yes. Yeah. So when you keep doing this, you will get a delta A at some point of time equal to 0, right? And all these, so when delta A gets to 0, I mean it won't become 0, but you'll have some tolerance limit. You will say 10 power minus 5, 10 power minus 10, some tolerance you will fit, you'll say which is acceptable value, okay? And until you get that convergence value, you can iterate this, use the correct position, okay? Use the correct position, get the new force, get the new acceleration, and then you get the difference between between two consecutive iterations, you get what is delta A. Using the delta A, again go here and then calculate the new positions and then repeat over and over, okay, and then you get a again you can, I mean in fact there are a lot of analysis being done on what is the optimum number of iterations, how many iterations are required, all that is actually worked out. But like I said, in MD simulations we are not worrying too much about the this looping behavior. We just do only once, and because if you look at this particular problem, every time I do for a correction, I have to do force calculation. So that is like n square operation, and I'm not we cannot afford to do multiple iteration, because every time I iterate I have to get force calculations, n square calculation. It's going to be extremely time consuming. So whenever we use predicted corrector method in MD, we use only one step correction.
Okay.
Yeah.
And just the last thing, why do we need larger delta T in this case?
That is because if you think about basically let's say the simulation time, okay, let's say you want to simulate the system for let's say 1 nanosecond, okay, and then you have a fixed computing time. Let's say you can do only for the CPU time available, maybe let's say 1 hour, okay, you got only 1 hour time. Within that you want to reach 1 nanosecond, okay. So this basically tells us that your delta T should be some number of time steps, sorry, n times some number of time steps times the actual real time per MD step should be equal to 1 nanosecond, okay. So now if I use right, Okay, so maybe I'll not use this because I think this is not correct. So what I was trying to say is that if you have a fixed amount of time, 1 hour, and then you want to reach a certain number of real simulation time, the larger the delta t step you take, quicker you can actually reach, right? So that's the reason we say that you want to have a larger delta t. It is also if you just think about simply solving an ODE with a delta t as a time increment, the larger the delta t use, the less number of steps you need to reach the actual time, right? So that's the reason I said delta t should be large enough.
So we want our algorithm to give us good predicted, accurate predicted values without compromising the accuracy.
Yes.
And in less number of steps.
Yes. So it's basically a competing requirement. On one hand, I say accuracy will be more when delta t is very less, because we are basically advancing. We are making approximation very close to the time t. On the other hand, we say for practical purposes, I want larger delta t so that I can do more number of steps in a given time, or I can reach longer simulations in a given computing resource. But these are competing requirements. So we have to make a compromise between these two.
So we need an optimum delta t.
Yes. In fact, what we generally do is we do simulations by changing the delta t, and what will happen is that typically if you define certain error function, okay, so let's say some error function we define which can be a global error or a local error, you will have typically some sort of behavior like this. So when you have very small delta t, accuracy maybe is good, but then you'll be doing very large number of simulation because your delta t is very small, and this will add up a lot of rounding of error that will add up to the global error. And then if you come down, if you increase the delta t, what will happen is accuracy is not very much compromised yet, but then this rounding of error because of large number of simulation step will come down and you will reach some optimum value. And then if you keep increasing delta t beyond, then the accuracy will be compromised, and that will lead to error propagation, and you see another behavior like this. So typically one would do delta t effect on certain global error function, and you see what is the where this error function goes through minima, and then pick up that as an optimal time. This will again depend on a chosen or a particular given algorithm.
Okay, sir.
Yeah.
Thanks.
Sir?
Yeah.
Sir, if we want to calculate some phenomena for which the time scale is very less, for that time step we cannot do that, like vibration.
Yeah, of course. Yeah. See this.
Then there will be error.
Yeah. See, that's what I'm saying. So the delta t that we are choosing has to be much smaller than any correlation time that you have. I mean any physical time that is involved in the system. So that's why if you're talking about, let's say, a system where there's a bond vibration is present, and then the motion of the molecules are also present in terms of diffusion and other things, then what we do is then your time scale will be limited by the shortest frequency, whatever the shortest time scale involved in the physical process, in this case the bond vibration. So at that point what we do is there are many ways we can handle this. One is to use a dual time step MD. You can treat a smaller time step for the bond vibration and the larger time step for the molecular motion. That's one way. And the other way is, in the larger time scale, you can imagine that the bond vibration can be averaged out. You can think of the bond to be having a constant value of bond length. So you don't worry about the local fluctuation of the bond vibration. Just treat them as a rigid molecule. So there are different ways to approach such a stiff system.
Okay, sir.
Yeah.
Okay. Sir, is there stability here, instability that we are seeing in this picture? Is it exponential?
Yes. Yeah, I mean, actually there is a nice theory to explain all these things. It's called Lyapunov's instability. Lyapunov. It's called Lyapunov exponent or Lyapunov instability, and it is not given in the textbook that I follow, but it is there in Frankel and Smith, and then if you can just go to Wikipedia and find this also. So Lyapunov is the one who actually explained this instability having an exponential behavior.
Sir, one small doubt.
Yeah.
In the first case, what is B in the
so that is basically the third derivative of position. The B is basically the third derivative of position. Yeah.